Our first speaker today is Dr. Leslie Gertsch from the Missouri University of Science and Technology, and today she'll be presenting for us research on water ice extraction from regolith.
Hello. I've shortened the title a bit from what you see in the agenda, just because that was an awful lot of words. But basically, I'll be talking about technologies that are designed to achieve certain capabilities. And the goal is to transform natural materials into materials that can be used in human endeavors, in this case on the moon. To do so, these technologies that I'll be giving examples of use current understanding of physical sciences and potentially also biological sciences, as they are currently experienced by us in a very narrowly constrained environment of the surface of this one planet, the Earth. Effectively transferring these capabilities to other bodies like the moon means rethinking how we apply the fundamental sciences that we're using these technologies to that particular goal. Next slide, please. This is just contents. A fundamental criterion for science applicability in extractive engineering is utility for separating the desired material from all the other materials that are found with it. And that also means taking advantage of natural segregation processes. That's why we're looking at the poles of the moon. So although this presentation actually focuses on specific technologies, please be thinking about the capabilities that they are intended to achieve and how current technologies do so, and how the lunar and ultimately Martian environments can be used to do so in new ways. So each example that I give cites a reference that are listed at the end as a starting point for any additional exploration you'd like to do for that. Now, due to the short duration of the talk, I'm only showing some examples of recent research. We're not talking about mineral-bound or mineral-incorporated feedstocks for water. We're talking only about water ice. We're not talking about products other than liquid oxygen and liquid hydrogen. We're not talking about historical technology development, even though it's very informative. And we won't also be talking about the specific science needs for achieving the desired lunar capabilities, which is a part of an important part, but only a small part of the science of space resources. Now, the examples I'm going to be given are divided somewhat arbitrarily into studies of systems and of major technology subsystems. So next slide, please. All right, the concepts that we're going to be looking at here are typical of many, and they're being developed on a continuum from in situ extraction of the water to ex situ extraction of the water. There's a wide range of maturity in these examples, a wide range of, as I said, in situ versus ex situ. The talk is biased actually toward government, primarily NASA-sponsored research, and away from privately funded commercial research, only because the latter tend not to publish quite so much. So there's a bias there, and I want you to be aware of that. There's wonderful research being done commercially, but it's not quite as available. Let's see, now several of the presentations we've already seen today, and some that are actually going on in parallel sessions right now, address the topics that I'm bringing up in this particular talk. So you may want to look through the videos that are available once we're done. I think they said they'll be available in a week or so. Now, the examples that I'm listing here, show the range of approaches. The evaluation criteria I just mentioned here, sometimes they're called figures of merit. They are critical for evaluating the research and development of these technologies for lunar mineral production. But as I say, we won't talk about them here. Now we're going to go into the examples. Next slide, please. This is the Colorado School of Mines concept of thermal mining. It's a very thoroughly updated version of a concept that's been around for a little while, but they've added some new wrinkles. They've got study teams focusing on various aspects of this mining method. It's primarily in situ, at least so far as the initial extraction of the water. As many of you have seen in other presentations, There's a large transparent dome. You can think of it as a tent placed over surface ice deposits to capture the volatiles that are mobilized by energy beamed into that dome. Then they're looking at what rates of volatilization can be achieved, and very interesting. Of course, they're all interesting, I must say. Let's see. Next slide, please. This is a plume that Maston, or a study that Maston is doing, taking advantage of the observations that rocket exhaust has been shown to excavate regolith both on the moon and on Mars. Recent Chinese landing on the far side showed that on the moon. Let's see. Now, this concept uses a manifold similar to the thermal mining concept, also with cold trap collection. The difference is that this concept could excavate to a potentially much greater depth. You may have heard Dr. Schmidt talk this morning about the almost 3-meter depth of core that they were able to achieve on Apollo 17. But that when you're talking ore body definition, ore body models, that is just skimming the surface. And this could probably go much deeper than that. Next slide, please. This is a honeybee robotics concept, planetary volatiles extractor, which you'll be seeing a talk on coming up next, I believe, or at least certainly this afternoon. So I'm not going to spend much more on that. It's in an in situ approach. Next, please. This is an approach by Transastra. It's an in situ approach similar to the thermal mining of CSM. This is an image from their proposal for a recent NASA grant. They're going to, however, bring in the wrinkle of using different and tuned different wavelengths of the energy to hopefully increase the range from which the water ice can be pulled from regolith in situ. It's an example of research that's both for profit and also funded by government. So it's a hybrid there. Next, please.
2 minutes, by the way.
Okay.
2 minutes.
All right. Well, let's skip past this one. Next slide. Okay. The process technologies. Now, many of these are being studied as part of the systems we've just looked at. And the approximate order in which they'd be applied is separation, purification, breakdown, which I was asked to talk about electrolysis, but there are other methods, and liquefaction. So let's go on to the next slide. Okay, the first bullets are actually describing surface mining as a separation technology. It's a primary separation technology. It's implicit in a lot of the NASA plans, so I don't have an example of that, but I do have, next slide, an example of an auger dryer, basically a continuous spiral conveyor with a heating source incorporated. This particular one was set up for Mars ISRU studies and is being adapted now for lunar studies. Next slide. Purification technologies. I've listed some of the very basic approaches that are used for purification. Purification covers a lot of stuff. Impurities are things that can poison the downstream process, degrade equipment, shorten their working life, things like that. But remember that impurities can also be byproducts or co-products as long as they don't interfere with the primary product, which is oxygen or hydrogen. Next, please. This is from a study by Paragon that's looking at using management, basically setup and management of the cold traps, and all these processes have cold traps, by restricting the temperature and pressure of that. They've actually gone into engineering solutions for problems. Next slide. Electrolysis is one of, as I said, several processes. There's thermolysis, photolysis, but electrolysis generally these days has 4 types. I've put out 2 types. Jerry Sanders this morning mentioned another one, alkaline, which is the most mature one on Earth. These diagrams just show what they are. Generally, depends on what materials you're using for the membranes. Next slide. And this is an example of a system that Oxyon and the School of Mines are developing for stacked solid oxide electrolysis to produce hydrogen and oxygen. So this is very focused on what we're talking about today. Next slide. And this is a slide showing the 5 major types of liquefaction technologies that are being studied for use on the moon and elsewhere in space. I don't actually have a specific example, but the Johnson et al. Paper gives some good information. Next slide. And these are the references. So I urge you, if you've got a wonderful revolutionary new idea, please research previous R&D. You may find problems that you hadn't expected. You also may find good suggestions for future work. Next slide, and that's my last one. Thank you very much.
Okay, thank you.